Welcome back, Physical Science 20. This is the beginning of HT2, and for this we'll look at section 16.2 from a textbook I got, heat in chemical reactions and processes. So here we look at chemical reactions and looking at the energy involved with them. First of all, one thing we should look at is the word exothermic. We can think of EX standing for exit, endothermic, EN for enter, exiting, entering, and that'll help us make sense of things to come here. So if we look here, virtually every reaction and change in physical state either releases or absorbs heat. Exothermic reaction is one in which energy is released, so it's exiting an area. And endothermic one is which energy is absorbed, or the energy is entering an area. So of course, thermochemistry is the study of heat changes that accompany chemical reactions and also phase changes that we saw in HT1. If we look at how we can represent exothermic and endothermic reactions, here's one way. So for example here, this is the rusting of iron combining with oxygen to make iron 3 oxide, plus 1625 kilojoules. Now what this means is that as iron combines with oxygen, it makes iron oxide and heat. Now what this heat energy is, it's being produced, so it is actually being released. So if we see a heat term on the product side of a chemical reaction, it's exothermic, meaning that it's produced. It's on the product side, it's produced. So it's exothermic. In chemistry and thermochemistry, we used to talk about the system and surroundings and universe. Universe consists of the system and surroundings. System, we can think of that as where our reaction is happening, and surroundings is everything around it. So in this case of rusting iron, the reaction is occurring in the system, surroundings is around it, so heat would be exiting the system and going into the surroundings. Okay, so that's exothermic reaction. They talk about a heat pack here too, very similar. It reacts with oxygen and releases heat. The system there would be the heat pack. The surroundings would be your hand. So heat goes from system to surroundings, and of course we perceive that as heat energy. Endothermic reactions, it's reversed. Heat flows from the surroundings to the system. For example, if you dissolve ammonium nitrate in water, the temperature of the water decreases. This is the equation for that process. So it's a reaction that involves energy, and I think we'll maybe do this in class. We'll do a demo in which you can actually see that. And of course, cold pack, ammonium nitrate dissolved in water, or ammonium chloride does that. The reaction is happening here. It needs energy to occur. Where does it get the energy from? The surroundings. What's the surroundings? You, or your leg, or your hand. So if the heat term is on the left-hand side, that means it must be a reactant. We need heat in order for the reaction to occur. So that is referred to as an endothermic reaction. So of course here the surroundings is your kneecap, and then it goes to the cold pack. Enthalpy and enthalpy changes. The total amount of energy a substance contains depends upon many factors, some of them which aren't fully understood. And of course, we're more interested in changes in energy during reactions than the absolute amounts of energy contained in reactants and products. So I use that word enthalpy. What that really means is the heat content of a system at constant pressure. And of course, we're looking at changes in enthalpy. So as a reaction happens, how much energy is released or how much energy is absorbed. So we're looking for enthalpy of reaction, which in chemistry we refer to as delta H Rxn. The Rxn means reaction. The Greek symbol delta means change in. So change in enthalpy. And of course, to find the change in anything, you're taking some final amount minus an initial amount. So that's what we look at there. If it's a chemical reaction, that final thing we're talking about is products. The initial thing we're talking about is reactants. So it's the difference between products and reactants. Okay? Other ways we can represent enthalpy. So here we had this rusting of iron. The energy is being produced. Another way we can represent that is just have the equation without the heat term in it, and this off to the side right, delta H of reaction is negative 1625. Now the negative there implies that we're losing heat. The system is losing heat. Heat is being produced. Just like if you had $20 in your pocket and you lost it, you would have negative $20. So we can represent exothermic reactions in those two ways. Heat is released, so it's indicated by a negative sign if we just write it off to the side. Also, we can represent in terms of a graph. Now, I apologize, this is a little messy. I have another handout here which will clarify this a little bit better. But if we imagine this as a graph, as the reaction progresses, to represent exothermic reactions, energy being released, we can think of the reactants, iron and oxygen. If you look at the green part here, they have a certain amount of stored energy. We're making iron 3 oxide, which has a lower amount of stored energy. So we have extra heat that we don't need. It just simply gets released. It's like saying if you had $50 and we're buying a t-shirt that's $20, you'd have 30 extra bucks. Okay? Endothermic reaction is vice versa. We need to take in heat here. And if we look down here, our ammonium nitrate example there, ammonium nitrate combined with heat produces my products. And if I wanted to represent that in a different way, outside of the equation, it would be delta H Rxn is 27 kilojoules. And so endothermic, we need to absorb heat. So we have low energy reactants, and we want to make products that have a higher stored energy or potential energy, so we need to add heat in. So those graphs kind of show you an indication as to how that works. Downward arrow means exothermic heat is released from system to surroundings. Upward arrow means I must absorb heat when going from reactants to products, so that's endothermic. And then here's just a little summary of what I had here. If we're representing these heat terms just off to the side, they're positive or negative depending upon whether it's endothermic or exothermic. So earlier we defined Q as heat gained or lost in a chemical reaction. When the reaction takes place at constant pressure, the subscript P is sometimes added to Q, the enthalpy change, or in this case we just simply replace that with delta H. Okay? I have another sheet here which kind of summarizes that too in kind of a neater fashion. If enthalpy change is in the equation, you may want to highlight that. Exothermic, it's on the right, on the product side. Endothermic, it's on the left, the reactant side. So we have that little note there. If it's exothermic, it's on the product side because it's produced and released. Reactant side, if it's an endothermic, because we have to absorb it. If we have it out of the equation as a delta H value off to the side, of course a negative indicates that it was released, it's lost, it's produced, so it's exothermic. If it's positive, that means we have to add it into the system, so it must be endothermic reaction, it has to be absorbed, it's part of the reactants. Okay? And looking at some neater graphs there too, the enthalpy level diagram that we call it. Exothermic reaction, you have high energy reactants making low energy products. So when the bonds are broken between the reactants and reformed to make products, we have extra energy, it's released. Endothermic reaction, we have low energy reactants making high energy products. We need to absorb extra heat. It's like saying I have 20 bucks, I want to buy something that's 50, I need to absorb 30. Okay, that's basically the difference here between endothermic and exothermic reactions. I have a few questions here. I had an assignment I'd like you to look at. So why does delta H for an exothermic reaction have a negative sign? Explain what is meant by delta HRXN. Why is it sometimes positive? So why is it negative? In describing a chemical equation, what is meant by system? What is meant by surroundings? If the enthalpy change for a reaction is negative, what does that indicate about the potential energy of the system before and after? So we're talking about this. Potential energy before compared to after in order to be labeled an exothermic reaction, I believe it said there. Or a negative. How does the enthalpy of the product compare with the enthalpy of reactants in an exothermic and endothermic reaction? And then sketch just a random enthalpy versus progress graph for an endothermic reaction. Okay, and the next part will be 16.3, which will be in the next video. And we'll see you soon.